All right, here we go. We are doing one of our flip classes today. It should be Thursday night, and you should be watching this video, or probably for some of you Friday morning, or maybe even Friday during class. In any case, we are going to do the isosceles, or we're going to use, not just do use the isosceles and equilateral triangles. Interestingly enough, you could have used these particular theorems that we're going to talk about today on that worksheet packet, as some of you call it, that I gave you the other day. This will, again, it is an extension of what we've already learned as far as proving different things. It's more arsenal, more tools to go into our suitcase or our bag when we are trying to solve and prove different things. All right, so let's go ahead and jump right in and take a look at these isosceles triangles, okay? First of all, with an isosceles triangles, you already know from your vocabulary, okay, that you have two legs that are the same side, or two sides are equal. We call those sides that are equal the legs. Okay, so from now on you can refer to the legs as the two sides of an isosceles triangle that are congruent. Okay, so in this case they're both 8.9, and that's the case here. And if I move this around, they change with it. Okay. Now the other thing we have is your base. Your base is the non-legs. Okay, the non-congruent side. Now, is it possible for all three sides to be congruent within your isosceles triangle? Yes, the answer is yes. Hopefully you got that, because if you have an equilateral triangle, all three legs are the same, or all three sides are the same, are congruent, and equilateral triangles are by definition isosceles triangles as well. Okay, it's just that the other way, isosceles triangles are not always equilateral triangles. Okay, so it is possible for this base to be congruent to the legs, but for isosceles purposes, all we need is two legs that are congruent, and then of course your base is the one that sits on the bottom, or the one that's the non-congruent side, if you will. Okay. You also have two angles. The two angles here, you'll notice, are congruent, right? If you look closely, and you should have some experience by doing this from the Pythagorean theorem, but the angle across from one of the legs and the angle across from the other leg are both congruent. Okay, so what conjecture can you make? That's right, you can make a conjecture that states that in an isosceles triangle, the two angles across from each leg are congruent from one another. So always, if this is congruent to this, then these two angles are congruent to each other. We call these the base angles. The base angles will be congruent. So if the legs are congruent, creating an isosceles triangles, then your base angles will also be congruent, and that is something that will help you when you're going to do proofs. You could have used this, like I said the other day, on your homework. Okay. The angle that is across from the base itself, so here's the base, AC is the base. The angle across from the base itself is called the vertex angle. Okay, so basically you took what you learned in middle school, elementary school about isosceles triangles. Now you're adding more dimensions to it. You're adding the vertex angle, the base angles, and the leg. Okay, so the vertex angle may or may not be congruent. Okay, so, and we'll talk more about that in a minute. So if the legs are congruent and the base angles are congruent, okay, that's what we're saying down here. Legs and base angles are congruent. Okay, and as always, if you have any questions, please write those questions down and come see me in tutoring. Now, the isosceles triangle gives birth to two more theorems. Okay. And the first theorem is the one that we could have used on our homework, is the base angle theorem. That basically says if two sides of a triangle are congruent, creating our legs here, right, then the angles opposite of them are congruent, or the base angles, right? So if your legs of a triangle are congruent, then the base angles are congruent. Okay, that's kind of how you could use the terminology from the isosceles triangle. So that's the base angle theorem. And then, of course, you have the converse. If you remember back to our lessons over converse, contrapositive, blah, 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 okay? The converse is basically flipping it around. If the base angles are congruent, then the sides opposite of them, the legs, the sides opposite of them are also congruent. So two more theorems that if you have hopefully took from my lecture the other day, that you'll put adding to the back of your vocabulary notebook so that you can go ahead and commit those to memory. Okay? So base angle theorem, two sides of a triangle are congruent, and the two angles opposite of them are congruent. The converse of the base angle theorem says if the base angles are congruent, then the sides opposite of them are congruent as well. All right, outstanding. Now, I do want to tell you one thing before I move on. I want to tell you that there are also, isosceles can come in a couple different sizes and shapes. They have different hats. You can have an isosceles right triangle. If you have an isosceles right triangle, okay, where is your vertex angle? Okay, that's right, your vertex angle. If you use common sense, which I know as somebody, Brooke Bover, told me today in fourth period that not all pre-AP students have common sense, which is understandable and completely fine. But if you use your common sense, you would know that if you have a right angle, that means you have 90 degrees, right? Okay, you can only have one right angle in a triangle. Otherwise, you cannot split the triangle three ways with 290 degrees because you've taken up two angles that equal 180 degrees and you need a third angle for a triangle, right? So our vertex angle would be our right angle in that case because that would be the side opposite of the base. That's the side opposite of the side that's not the same. What would the angle measures be for an isosceles right triangle? Yeah, that's right. The isosceles right triangle would have a 90 degree and a 45 degree and a 45 degree. They call those 45, 45, 90 triangles, okay? We use those a lot, and we can use some things with trig functions and stuff to help us figure out like side measures and stuff from a 45, 45, 90 triangle. Okay. You can also have an obtuse isosceles triangle. If you have an obtuse isosceles triangle with the same thought process that you had on the right isosceles triangle, where would the vertex angle be for an obtuse isosceles triangle? Yeah, the obtuse angle would be the vertex angle, right? Okay, because you can only have one obtuse angle. All right, just a couple extra nuggets for you. You might want to write that down for later use because those are those easy questions that you miss on a test or a quiz or a homework because you know the answer but you're not really sure and so you kind of end up guessing. So go ahead and commit that to the old noggin. All right, moving on. Now we have our friendly equilateral triangle. Okay, in our equilateral triangle, you'll notice that each side is equal. Thus, equilateral triangle. Okay, equilateral triangles, you may also notice from this picture here, this diagram, are equiangular, meaning all sides are equal. That makes sense, right? Because we said earlier in the isosceles that if the two sides are congruent, then their opposite angles are congruent. So now you have three sides congruent, so the opposite angles are all congruent. So this goes with this angle, okay? Well, it matches this angle, that's 12, they're congruent, so this angle across from it must be congruent. Well, heck, this is congruent to the rest of them, so this angle across from it must also be congruent. So in the equilateral triangle, all your angles and all of your, whoops, didn't want to do that, all your angles and all of your, so notice I'm changing the size of your triangle, but I did not change the angle measures, right? Because the angle measures don't change, they're proportional. But in an equilateral triangle, all your sides and all your angles are all congruent. So from our friendly equilateral, and they all have to be 60 degrees. Why? Well, because 180 divided by 3 must be 60. All right, very good. Okay, try to instill some common sense in there for you. That's a Brooke Bover special. Okay. All right, now, with that being said, from the equilateral triangle, we get the birth of the equilateral corollary. Okay, corollary, such an interesting word. Don't use a whole lot of these. Not a common word in English vocabulary, but a corollary basically is kind of like adding. You know, it's part of, it's an extra part in addition to. And the reason it's a corollary is because the equilateral corollary states that if three sides are congruent, then three angles are congruent. Okay. Not much different than what we saw back up here. If two sides are congruent, then the angles opposite of them are congruent. Okay, so what that is doing is we're saying, okay, since we know that from the base angle theorem, okay, since we know that from the base angle theorem, then we're going to add and say, okay, with that being said, we'll add this equilateral corollary, just extending on that base angle theorem and saying, all right, if three sides of a triangle are congruent, then three angles are congruent as well. Pretty simple. Okay. All right, moving on. So here's where we're going to apply these bad boys. All right, let's take a look here. We have what kind of triangle? That's right. It's an equilateral. That's an equiangular triangle, which therefore, because of our converse, we know that it's an equilateral triangle. With that being said, we know that all three of these sides are 4. So we know that y equals 4, right? Okay, if y equals 4 and this side equals 4 here, this side right here is reflexive within these two triangles. And with that being said, since they're reflexive within these two triangles, you now have an isosceles triangle based on the angles being congruent here. Two angles are congruent, therefore these two legs, opposite of the angles, are congruent. We just said that these are congruent to 4, so this must be 4. So x plus 1 equals 4. So I know now that x must be 3. Pretty simple, right? One more basic example. Let's take a look here. Here we have a right angle. Now we have what kind of triangle right here? What kind of triangle is this right here? Yeah, that's an equilateral triangle. Excuse me. Looking at the wrong angle. This is a... Keep clicking on the wrong things. This is an isosceles triangle because we see that two sides are congruent. 1, 2, those are congruent. The base right here is not congruent to the other two sides. So this is an isosceles triangle. Over here, on the other hand, we have that all three of these sides are congruent, thus the two markings. And since all three of these sides are congruent, you have an equilateral triangle. So if this is an equilateral triangle and all three sides are congruent, x must equal 60 degrees, right? Okay, if x is 60 degrees, that means 60 degrees is also right here, okay, in this angle right there. Okay, so if x is 60 degrees right here, and this is a 90 degrees, what does this angle measure? Right, this angle measure right here is 30 degrees. Now, is this one of our base angles? Yeah, it's 30 degrees. It's opposite of this y here. This is 30 degrees, opposite of this y here, or this here. Okay, now I'm looking for y, which y should be, excuse me, y is the vertex angle. So I'm looking for the vertex angle. So here, this is 30, and this is 30, because these are congruent. This is 30, because 30 plus 60 is 90. So this is 30, this is congruent to this is 30. So 30 and 30 is 60, how much is left? Well, 120, right? So our vertex angle is 120 degrees. And that's pretty much it for section 4.7. Again, if you have any questions, please feel free to come see me. I hope you enjoyed it. Have a good one.